we proved the lemma. So basically, yeah, maybe we have our domain on a hexagonal lattice. We have three marked points on the boundary, let's say A, B, C, or A1, A tau squared. So I've simplicity denoted them by cube roots of unity. Now, what we defined function, well, let's say H1 is the probability that H1 of Z is the probability that there is a crossing which separates Z and A1 from two other boundary points. And what we proved that, well, there are three functions like that, H1, H2, H3. The main lemma last time was that basically discrete derivative of H1 in some direction. So discrete derivative in direction alpha of H1 of Z. First we wrote it exactly as what I denoted D plus H1 of Z minus D minus H1 of Z. So those were three arm probabilities. So it's basically, if we take derivative in this direction, then the first one is the 3-arm probability. Then the first one is 3-arm probability for this triangle, and the second one is the 3-arm probability for that triangle. So there were pictures like okay, so what was here that Z prime belongs, and so here there was a so this point is below and this point is above. Yeah, so it's something like that. Oh, the other way around. Yeah, so it's this one is something like this. So it's a 3-arm probability for this bottom triangle, and this is 3-arm probability for top triangle. So it was this guy. Okay. And then this was approximately equal to D tau alpha H tau of Z, and approximately equal to D tau squared alpha H tau squared of Z, and approximately equal because we can perturb the covers of 3 arms around each of these triangles. But then if here we had D plus D minus for one rhombi, then when we shift direction we'll have it D plus for 1/2 of one rhombi, D minus for 1/2 of another, so we slightly move it apart. Okay. So let's for the time being assume that well, those are like Cauchy-Riemann equations. So what are the usual Cauchy-Riemann equations? So a small remark is the usual Cauchy-Riemann. They tell you that derivative of a function f in the direction alpha is times I is derivative I the direction I alpha of a function f. Or if you put tau, it means tau derivative in direction alpha of f is derivative in direction tau alpha of f. So when we have this derivative, so and the first one, you know, the usual way you rewrite it, f is say x plus iy, then you rewrite it the derivative of x, well, f u plus x derivative of u is related to y derivative of v, which is 90 degrees rotation, and vice versa. So similarly, you can rewrite it in terms of projection on 3 vectors, only those are linearly dependent. And to get an analytic function, you should just concode from h1, h tau, and h tau square something which satisfies this relation. And you can do it using these things, so we'll do it later. So from that it follows that you can construct an analytic functions from h tau squared, and h1. So basically you should think that you have three harmonic functions, so these functions will be harmonic. They are projections on three linearly dependent vectors of something. So you can either take two projections and you take coefficients which would be here include square root of 3 or something, because you have an angle 120 degrees, or you can utilize all three of them if you wish. There are clever ways to do it, so we'll see it later. But yeah, for the time being, let's maybe okay, let's assume maybe let's assume the following proposition. So suppose h1, h tau squared tend as mesh of the lattice tends to 0 to some functions h1, h tau squared. Now, what do I mean by tend? So we have functions which are given on a lattice, and in the limit I have functions everywhere. So we'll see later that these functions are actually Hölder continuous, so you can think of this function on the lattice as defined everywhere piecewise linearly. So it's defined at all centers of triangles, so we define in between piecewise linear, just split everything into small triangles. So yeah, our function is, so this defined piecewise linearly. Then, well, for example, the following functions would be analytic. h1 plus h tau squared is analytic, and g is h1 plus tau squared h tau plus tau h1 is analytic. So there's
I'm wondering about this function f. Are these little h functions not real valued?
They're real valued, yeah. Well, then it means what is a real valued function which is analytic?
Constant.
A constant, yeah, it's a constant.
That's what I was wondering.
But yeah, that's a good remark. This is actually a non-trivial statement that which I mentioned the first time around, that these three functions, each of them is probability of having such or such crossing, and the sum of three probabilities apparently is always 1 in the limit, and I don't know any other proof of it. So I don't know like an easy consideration which tells that we flip covers here, flip covers there, and we sum these three probabilities to 1. There is an easy consideration on the boundary, but none. Okay, yeah. And I mean, of course, from that you can also take their differences. For example, if I put what would be, for example, f minus g, or well, let's say let's put tau f minus g. So tau f minus g is tau h1 plus tau h tau plus tau h tau squared minus h1 minus tau squared h tau minus tau h tau squared. So this cancels out. So you get tau minus 1 h1 plus tau times 1 minus tau h tau. Well, we can cancel out this one, so we get also things like h1 minus tau h tau is also holomorphic. But this is basically, I mean, if h1 and h tau are projections of some complex vector on 1 and tau vectors, this is how you can reconstruct it. This or that also. So these two are how you reconstruct if h1, h tau squared are projections of something on a complex vector. That's the two ways how to reconstruct it. You can take this, or you can take this and multiply by something. Okay, so we'll just assume this for the time being. We'll prove it later. So it's and let's do everything modular that. So I'll do a sequence of lemmas. So that was, let's say, lemma 1. So now we need a few lemmas which ensure that we can make this thing. So we'll play the same game as always, that we prove precompactness, and then we do it with subsequences. So the lemma for precompactness is the following, that there exists constant C at bigger than 0, so that h of z minus h of w, well, any of these functions h for any lattice, so that for any epsilon, the difference is at most c times z minus w to the power eta. So basically this means that H alpha belongs to Hölder eta class uniformly, or norm of H alpha in Hölder eta is no more than constant C. So the proof. So H alpha z minus H alpha w. So again, this is at most. What is the event that if we have 2 points, one of them is cut by a crossing and another is not? It means that there is a crossing which passes in between them. So there is a crossing which crosses this bow. Or the other way around, there is a crossing which crosses this bow with a twist. So it's, because I put absolute value, let me just put the same picture with a twist. So it's a very rough estimate. I don't even draw the third arm. I don't need third arm, so I don't even draw it. But in principle, you also can say that there is a third arm.
Should it be minus?
Yes. Sorry?
Should it be minus?
Oh no, but I put absolute value. Yeah, so I just need a crude estimate. So it's. Now, well, in principle, I could just say that it's something like that times 2. And now there are different things. I mean, first, where constant comes from. I have never specified the size of my domain. So now I have so the size of this bow. So this bow is the size of the bow is z minus w. And by Russo-Seymour-Welch theory, if I put a big annulus, I would have small probability of having a few arms. So the question, can I put a big annulus or not? And what I claim that if z minus w is sufficiently small, you can put a big annulus at least for one of these 3 arms. Yeah, so maybe I'll do the third arm anyway, just for simplicity. So what can happen? So assume that the distance between any 2 points AI, AJ is at least constant C, and we have this small bow. So it will be so basically the small bow will be away from one. The small bow will be away at least from one of these 3 sides. It cannot be close to all the 3 arcs simultaneously. So it's so for any position of this small ball B. There exists an arc, one of these arcs, let's say a tau, well, Aj, so that distance at least C minus this thing, well, let's say C minus Z double. So it's the picture would be something like that our bow is here. And if our bow is here, it's very easy to have this arm. But since it's big distance from that one, it's low probability of having that arm. So it's then this is at most twice probability of that. This is at most twice probability of having this breakthrough, this connection in an annulus where the inner radius is Z to the minus W and the outer is C minus Z minus W. And this is at most by Russo-Seymour-Welsh theory Z minus W to some power eta. Well, you should put a constant in front, which is different from that constant, let's say C prime. So this is just Russo-Seymour-Welsh theory. So that you remember, the Russo-Seymour-Welsh theory says that the probability of crossing a long rectangle or a thin annulus is at most its modulus. So that did you have such an inequality? Yes? Yeah. And we don't really care what the power is. So the power is actually 5/48 for one arm. And for 3 arms it's 4/3, but no, for 3 arms it is 2/3. And but we just care that there is some power, so we get ourselves into Hölder class.
Sorry, at second line here, any position of B blah blah, you're using kind of convexity.
No, I don't use. Well, okay. Yeah, sorry. Yeah, that is. I have to. Yeah, maybe I poorly. Yeah, the constant C should be not the distance of this. It should be. Let me see. So what should be the constant C? What is a good definition of a constant C? It should be some property of the domain. Yeah. So there is. Inner radius. No. Yeah. It's. Oh la la, yeah, that is, you are right, yeah, what Misha says is that there are domains like that you can position the annulus. Okay, so we assume that, so what is the...
Just keep the fact that neighborhoods of the arcs don't interfere.
Yeah, that the neighborhoods, so let C be the infimum of R such that R neighborhoods of 3 arcs are disjoint. So if you take R neighborhoods of all 3 arcs, for sufficiently small R, there will be no intersection between of all 3 of them. Because if for every epsilon there is intersection of all 3 of them, then yeah, the domain is degenerate and actually empty. Yeah. Yeah, you're right. Okay, so this gives us the Hölder norm. Actually, in Hölder norm also you add L infinity norm. So also the question why L infinity norm is no more than doesn't add something big here. So that's sort of clear. So there is a lemma 3. Well, this is just because H alpha is 0 on the bottom arc. Yeah, so this is because H alpha, so this probability of this connection is 0 on this arc. So it's so our function has Hölder modulus of continuity and also 0 somewhere. So it is then Hölder continuous with bounded norm. Okay. So this lemma 2 it allows us, so by lemma, so so we can do the following thing, that continue H alpha piecewise linearly with comparable Hölder norm. So basically our function H alpha, where was it defined? It was okay. So our function H alpha is defined at those points. So what we can do, we can just split, so we know it here, we split everything else into triangles in whatever way we wish. For example, well, I don't know, something like that would do. Well, anything would do. So split in triangles any way we wish and continue piecewise linearly. Or we can use some more regular way to split into triangles, something, so we draw this hexagonal lattice, and then for each hexagon we do like this. And then if we continue it linearly, the Hölder norm, I think it's, what is it? It's no more changes than by factor of 2. So this is actually a theorem of Whitney. It's sort of a theorem is a bit a stronger statement how you can, well, there is a theorem which tells you that if there is some compact set and there is a Hölder continuous function on it, you can continue it to whole plane to be Hölder continuous with the same norm. So that's the theorem of Whitney. And here it's a particularly easy case. So it's maybe an exercise. So basically what you do, you need to check that the Hölder norm stays the same. So basically when you compare two new points, what you do, each two new points, they are in some triangles. So to compare them, you compare two vertices of these triangles, and there is a Hölder inequality to other vertices, there is a Hölder to other vertices, and then you get that inside. It's also nice. Or you use triangle inequalities that here it is Hölder because it's just linear, here it is Hölder that it's linear, and here it is Hölder because our original function was Hölder. So it's still Hölder. So what we gain, that H alpha now are defined everywhere. So it's defined in the whole domain omega. Now the space of Hölder continuous functions, so the functions with bounded, the space of functions H where Hölder norm is bounded by C is precompact in the space of continuous functions on omega. So this is just the how is it called, Arcello-Ascoli theorem, that uniformly continuous functions are compact in so this is well, this is actually not even this is even compact. So it's so this is compact in the space of continuous function, or in any Hölder space with a smaller exponent. Which means, hence, from any sequence of our functions H alpha with some indices epsilon, we can always we can choose converging one. Bless you. H epsilon j alpha converges to H alpha. So it's the same trick as we did for SLE. We have compactness. Then it means that we can choose always converging subsequences. So instead of showing that our functions converge somewhere, it's enough to show that if they converge, then they converge where we want to. So it's enough to assume convergence. So so this is the big thing of this lemma. It is sufficient to show that h1, h tau squared are the desired functions given by a map to a triangle. So basically it's enough to show that if we have functions h1, h tau squared which have these properties that they are homomorphic with this sum, then they indeed are given by a map to an equilateral triangle and 3 coordinates in this map. So this is enough to show. Then of course we have to show the proposition afterwards, but that is what is enough to show. So it's enough to study their boundary conditions. Okay, so there now we have to do boundary conditions. Let me maybe do it here on the right. So let's say lemma 3. So if I take my domain, and these are the 3 points, let's say A alpha, A tau alpha, A tau squared alpha. So H alpha at A alpha is equal to 1, and H alpha on the arc, on this arc, is equal to 0. So if I take the probability that my point is separate from A alpha, then at a point A alpha is separated together with A alpha from bottom arc. On the bottom arc it's 0. At the upper point it is 1 in the limit. Well, the second statement is basically rather easy to prove because it's just literally so. So if I have a point here, there is there is no way to separate it. There is no way to separate it by a crossing. So if I, for example, just this is the boundary of my domain. So if I just choose point half a step below, then I cannot separate it at all. If I choose point a little bit above, then of course I can separate it. But then we get the same estimate as in lemma 2 by Hölder continuity. That would imply existence of an arm which touches boundary at exactly given place. So the probability will be very small, exponentially small, the same power. So the first probability of this is just exactly 0. If we put point half a step below, so that this is exactly 0. If we put it half a step above, then if we put it half a step above, so it's just one lattice step, let's say epsilon, then exactly by the same reasoning as before, probability is no more than c times epsilon to the power eta, which tends to 0 when epsilon tends to 0, so we get 0 in the limit. Now we have to estimate what is our function at the top. So what is the probability that you would have a cut which separates this top point from the other two. And here again we use Russo-Seymour-Welsh What happens if the mesh of the, of course, if the mesh of the lattice is finite, this probability is not 1, because there is always a small chance that everything is not yellow, everything is blue, so there is no crossing. But what we can do, we can draw an infinite sequence of concentric annuli with the same modulus, and each of them, so this is, each of them has a positive probability by Russo-Selmer-Welsh of having a connection. So if mesh epsilon, so mesh epsilon, we can draw logarithm of epsilon annuli, because we can draw it size 1, size 1/2, size 1/4, and so on till we hit epsilon. Each gives us probability bigger than some delta of a crossing. So we get that H epsilon alpha of A alpha is bigger up to a constant that 1 minus delta to the power log 1 over epsilon. But as epsilon gets smaller, the power gets bigger, so that tends to, no, wait a second, so it's, so the, yeah, 1 minus that, yeah, so it's bigger than, if we can draw at least 1, we are good. So the bad thing is that we can draw neither, so it's 1 minus constant 1 minus delta log 1 over epsilon. So that tends to 0 as epsilon goes to 0. So it tends to 1. So we conclude that H alpha of A alpha is equal to 1. Okay. So essentially now what is clear by now that we can figure out what is going on, because we have 3 projections of our functions on 3 vectors, and for each one of them we know that it's 0 on one arc, 1 on another, and then the other one is rotated, the other one is rotated yet again. So everywhere in the boundary we know we can pin down one of the 3 functions. So we have an analytic function for which everywhere in the boundary we know one of the projections. And this should be enough to determine it. So one can work with this. It's a bit easier, and this was a neat trick observed by Befara, to work with this with these 2 functions. So it's, let's say, Befara's trick. Let's consider function f. So f equal to h1 plus h tau squared is holomorphic. As you correctly observed, being real and holomorphic, it means that it is a constant. Also purely real. Then it means that f is a constant. And which constant? Well, we know that at this vertex, one of the functions is equal to 1 and 2 other are equal to 0. So there is this other function which is 0 and 1, and there is a third one which is 1 here and 0. So constant, so it's actually equal to a constant, and which implies that f is equal to 1, because f of a1 is h1 of a1 plus h tau of a1. So this is 1, this is 0, this is 0. Okay. It also means, interestingly enough, that so f is identically equal to 1, so that we have proved. Now f on arc a tau squared, f is equal to what? F is equal to 1, but h1 is equal to 0. So on this arc, h tau plus h tau squared is just equal to f, also is equal to 1. So we'll use it in a moment. Okay, so this is just f equal 1 is just a neat observation which tells you that if for any point in your domain you sum the 3 probabilities of having crossing like this, like that, and like this, it sums up to 1. And I don't know any other proof of it. Well, in the limit it sums to 1. I don't know any discrete proof which by some clever coupling would tell you that it is exactly 1. On the boundary, yes. On the boundary, by the way, it's possible to check it, so it's maybe a small detour. So suppose that I have a point on the boundary, and I ask that the sum of this probability and that probability is exactly equal to 1. And it's exactly equal to 1 because the way I've drawn it with the other arm in opposite color, those are dual events, so they sum to 1. So on the boundary, this is clear. So this is, well, alternatively, it is probability of, so alternatively what we have here is that probability of this event plus probability of that event is equal to 1 because they are complementary if we swap color here. Okay. Yes?
Does the fact for interior points hold for, like, on discrete level?
No, not as far as I know. I mean, even this you have to be careful on discrete level what exactly when they land. It does hold on the discrete level, but you should be sure that the corner of your domain is not a lattice vertex, so it's you should be careful. But inside, I don't know. I never checked actually, but it's well, it might hold because of some strange coupling, of some interesting coupling. So it's not totally out of question. Okay, now let's do the remaining part. So let's do the function g, which would do the job. What do we have with the function g? So it's let us write. So this is again our domain. Let's say a1, a tau squared. So on a tau squared, so we'll look at this thing. And now the good question whether I have chosen the normalization right. Oh yeah, I think I did. On a tau squared, so what do we get? We get g is equal to h1 plus tau squared h tau plus tau h tau squared. So h1 immediately is equal to 0. Now about the two other things, we know that they sum up to 1. So these two things sum up to 1. So this was just written here. Now h tau plus h tau squared is equal to 1. So this we can rewrite as x, well, let's say tau squared x plus tau 1 minus x, where x is between 0 and 1. So it lies on the interval between tau squared and tau. So if I try to ask where G maps it, so this lies, so the image of this arc lies on the interval between tau and tau squared. So this is the image of this arc. Now what happens with this blue arc? With the blue arc it would be exactly the same, only h tau will vanish. What will, wait a second, did I do that the other way around? No, I didn't. So if we do this arc, then another one will vanish. So it will be a line, an interval which which joins two other points. Now I think I might have somewhere confused the order. And then the third arc should go like that. Let me think. So it's, does it look correct? Did I put the correct numbers or not? So it should be so it should be 0, 0, 1, 0, 1. So it's between tau squared and tau, and the next, so if okay, yeah, and then the next, yeah, no, I think I'm correct. I think I have an impression that I changed the colors here, so maybe it's a good time for a break. But basically what we get here, we get an analytic function whose boundary values on three arcs, they lie within the three sides of an equilateral triangle, which means that this function is a map to an equilateral triangle. So it implies that, so we get G is holomorphic, and G of each arc, it belongs to the corresponding side of triangle, of an equilateral triangle. So these two things, by argument principle, imply that G is a map from omega, is a conformal map from omega to equilateral triangle.
So it is 1-to-1 because the winding number is 1, or?
Sorry?
It's conformal because the winding number is 1, or on the bottom?
Yes, yeah, it's conformal because the winding number is 1. So it's basically we have some map which maps our domain. Well, we have a holomorphic function, and what we know about the boundary domain, and our function is Hölder continuous. So boundary of a domain is mapped when you traverse it to some curve, which might be winding or not. But we know that the three colored arcs are mapped inside these three intervals. So we should get a loop which first, when you go around, which first goes here, then goes here, then goes here. And the only way to do it is indeed go here, then jump, then go here, then jump, then go here. So it will go around every point exactly once. So that's the argument principle. And from that, you imply that actually this indeed goes counterclockwise in a monotone fashion. So from the fact that just white is mapped into white, you get that it's actually mapped 1-to-1 because of the argument principle, because a posteriori it's actually indeed like that. But I mean, from probability, you can show that this thing is monotone, because when you move, then these probabilities change monotonely. So in principle, you could have chosen to prove it earlier, but you don't need to. So basically, the proof, once again, goes like that, that if we know that our limiting function is analytic, then we figure out the boundary values just by using different projection for each of the different sides. And then by argument principle, this is the map. So let's have a break. And then we'll finish, we'll use a little bit more about that, and we'll finish the proposition also. Here, switch the coefficients. It should be tau h tau squared. Otherwise, you get not an analytic function, but anti-analytic function. And I don't know why I've switched them. It's some stupid accident. So proposition should actually read like this. And then everything is, what I said is correct, yeah. Okay, so basically that's it. So the bottom line is that we have these three functions h. We prove that they satisfy Cauchy-Riemann, which still remains to be done. Then by compactness there is a subsequential limit. It is analytic, and then boundary values are enough to determine what it is. So this actually means that we have a map to an equilateral triangle, and it is given like that. And essentially, well, what h1, h tau, and h tau square are, they're just projections on these three cube roots of unity. So if we take h1, it's a linear function which changes between 0 here and 1 here. And h tau, it changes between 0 here and the other one is between 0 here and 1 here. And you can get the whole function either by summing three of them, or well, you can just take two with some coefficient, and that would do the job. Now, so this gives us the corollary, which is the Cardis formula. So probability of crossing in an equilateral triangle between bottom side and the part of the top side. If the part of top side is length u, then this tends, as mesh goes to 0, to exactly the length of this interval.
Why is h subscript something linear on the interval? I mean, this is what this is why it implies.
But we just proved that h is linear in the whole triangle, in particular on its boundary. We just proved that h is a real part of a function g, so it's linear in the whole triangle here. If our domain is triangle, it's just linear on the triangle, in particular on its boundary, it changes linearly. Yeah. So we prove that it is harmonic inside, then they deduce from boundary condition that it's linear inside, and as a consequence, it's linear on the boundary. It's we were after the values of h on the boundary arc, but what we did instead, we deduced its values inside. So I don't remember whether we gave as an exercise that it's the same as this big formula given by the hypergeometric function. Did I give it? Okay, so it's another exercise that because this is really easy, that the formula I have given is that in well, okay, exercise in half plane. So the same probability in half plane, so crossing from 0 u to 1, where now it's a small u, this probability tends to, and then there was this integral from 0 to u, 1 over c, 1 minus t to the power 2/3 dt. And then you have to normalize by the same integral from 0 to 1. So naturally this exercise only consists in checking that this function maps half plane to a triangle. And it's checked using argument principle, that you check first that this function is analytic. Well, this function is analytic as an integral of analytic function. You have an analytic function which have just two punctures at 0 and 1, well, 3, 0, 1, and infinity. So outside 0 and 1 you can integrate it and it is analytic. And then you can check what is its argument, and you can check that argument at 0 and at 1 rotates by 240 degrees. And then it's argument principle that it is, so if this is function is phi, so phi maps half plane to an equilateral triangle. And then you pull it back. So such maps, which are maps between polygons, are called Christoffel-Schwarz maps. So it's called. Just a small remark. So those are called Christoffel-Schwarz maps. And if there are 3 vertices, it's fairly easier. If there are more vertices, you put more poles for these vertices, but then you also have to carefully adjust the constants, because triangle, I mean, every triangle with angle 60 degrees is always equilateral triangle. But if you want to map to a square, and you got something with angles 90 degrees, you might very well have a rectangle. So you should also adjust some constants inside the integral so that indeed the lengths of the sides are the same. So if you are mapping to a polygon with 13 sides, there will be 10 parameters to adjust so that the sides, they have correct lengths. So then it becomes a little bit difficult, but I mean, it's rarely you need it you really need an exact formula. On the other hand, people who need it numerically, there are very fast numerical ways to do it, to adjust this constant. So there is very good software which plots it at no time. So it's Don Marshall at University of Washington. He has a program which does just that. Okay, so that's the proof of Carnot's formula for percolation. And once again, this thing, so Cardi gets it as a solution of a differential equation, of Riccati equation, a nonlinear differential equation that phi prime prime is equal to phi prime squared. So we get as a solution of a boundary value problem, which is a boundary value problem with oblique derivatives or with conditions on different parts of our function. Real part on one side, projection on cube roots of unity on other sides. Now, what remains for us to do is to prove this proposition, that these things are indeed holomorphic. And that's what I want to do. Now, so so how do we prove that something is holomorphic? Well, to prove that something is holomorphic, we can either prove Cauchy-Riemann equations, or we can expand function in a power series, or we can show that contour integrals are 0. And contour integrals are easier because you don't have to differentiate, you don't have to expand in power series, and you just deal with the function, not with its derivatives. So basically, well, let's say proof of proposition. So it is sufficient to show things like contour integrals of g or f are equal to 0, and well, it's enough to say, for example, all square contours or all triangular contours. So for, let's say, gamma, for any triangular contour gamma. Because any other, if you want to do some contour gamma which is not triangle, you can always approximate it by by triangles which get smaller and smaller and smaller. So you just take triangles like that, tie it, then each triangle you go counterclockwise around, the parts in common they cancel out, and then in the end you get as good approximation as you want by triangles. So it's enough only to do contours of some shapes. Usually in books they write square contours are enough, but we are on a triangular lattice, so for us triangular contours are enough. Okay, so let us do contour integrals. Let us do contour integrals of functions h. So h are discrete functions, so of course you have just discrete sums, not integrals, which will converge to Riemann sums for function h small. So how do I do contour integral? Basically I integrate Cauchy-Riemann equations inside. So the fact that so how do you prove in complex analysis textbook that contour integral of G is equal to 0? You take Cauchy integral, you take Cauchy-Riemann equation inside the contour, integrate them, and then it cancels out inside. You get a thing in the boundary. So we do the same with some these equations inside the domain. So let's do the following thing. So this is, so you should imagine that we have our domain omega. So instead of writing formula, I will just draw a picture. So this is our domain omega, and this is contour gamma. So this is triangular contour, or let's say size 4, for example, 4 by 4. And what I will do, I will just sum this, so let's, I will sum d alpha h over the following vectors. So I will just draw here a number of vectors. So basically, for every triangle which points downward, I took the vector up. And for every triangle which points up, I took the vector right and up direction. And if you sum difference along this chain of vectors, you just get differences at the top and the bottom, difference at the top and the bottom, difference at the top and the bottom. So let me maybe denote, what would be good letters for the boundary. So it's, let's say, A, B, and C, or A tau squared, A1. So basically, what we have here is that sum of H alpha on the AB minus sum of H alpha on the AC is equal to sum inside gamma of this d alpha H, but in this sort of snaky looking things. So it's basically continuous version of this would be that integral of H here with plus sign, integral of H here with minus sign can be written as the integral of the derivative along those lines. But since we don't have straight lines, we have to go zigzagging around. Now this we sum as d alpha plus minus sum d alpha minus, because we have to sort of, before we do bijection, we have to consider those two different pictures. So it would be, let's say, sum d alpha plus minus sum d alpha minus, which would be also with the same picture. But let me just draw it in a slightly different color. Let's see. Well, maybe. So that was in direction d alpha plus of, d alpha, if it was h alpha, let's say d beta, yeah, where there this vector is beta, yeah. So those are small vectors beta. So it's always the summation is inside gamma. And now we do this rotation trick, flipping three arms. So each of these arrows signifies that we have these three arms, and we can flip their colors, and we can write this as a, so it's d beta h alpha minus sum d minus beta h alpha. So this can be written as a sum of d tau beta h tau alpha minus sum d tau beta h tau alpha. And let's just check on our picture what happens. So these vectors, basically they get rotated 120 degrees to the left. So if we rotate all of them 120 degrees to the left, then for every triangle which points down, we have a vector which now goes like this. So we basically rotate 120 degrees. And for every white triangle, we have a vector which points there. So it's white triangles. Yes, it looks like that. So when we rotate this snaky picture, it rotates to similar picture, only triangle shifts a little bit to the left. So it's not the same, well, maybe I just did not draw a very accurate triangle, but it's not exactly the same triangle, because normally we don't need these things, but we would want another row here. So there is this sort of error when we rotate it. And the blue ones, d minus. So we also rotate them 120 degrees, but we rotate them not around there, not around this point where they start. We rotate them around their end point. So here we rotate also 120 degrees, but we rotate it around the end point. Here we were rotating around the starting point, and here we need to rotate around the end point. So we just do the same picture for every up-pointing triangle. We would have picture like that. And for every down pointing triangle would have picture like this. So it's
You need to draw errors on the bottom line. So,
You think so? Do I?
or are they these stitches?
No, I don't think, because I rotate them around their end point. No, I don't think so. I think I go because this it's, well, okay, it's basically a pictographic representation that what this blue arrow means. It means that we have three-arm picture around this triangle. So when we change color of arms, it rotates around its end point. I don't know. It's kind of either you do a picture or you write formulae, but essentially one has to check the accounting carefully that nothing breaks. But morally, the thing is simple, that we can, when we change function from h to 1 to h tau, we can rotate the direction in which we differentiate by 120 degrees, and we get some error terms, but we get them only on the boundary of our box. So here we shifted our box slightly to the left, here we missing one row here, and we have one extra row there. But basically, the conclusion is that this whole thing is sum of h tau alpha on this arc. So this arc is, what is it, BC, minus sum of h tau alpha on the arc AB, plus an error term. An error term is basically the order you sum over the length of gamma some terms, some things like d alpha, d beta, well, d beta h. So it's the error term, it's not inside the contour, it's only on the perimeter of the contour. No, not integral, sum. And we know that these three-arm events by Russo-Seymour-Welch, they have small probability. So this is at most by Russo-Seymour-Welch constant lattice mesh to some small power. So it's something small by Russo-Seymour-Welch, only summed the length of the thing. Now, how, if you have a sum, how do you get an integral from Riemann's sum? You multiply by the lattice mesh. So those are multiplied by epsilon. So mesh epsilon multiplied by mesh epsilon, we get Riemann sums. Riemann sums which converge to integrals. So what we then get here, if we multiply by epsilon, this will converge to integral on AB h alpha minus integral on AC h alpha, and this is equal to integral on BC of h tau alpha minus integral of AB of h tau alpha. And what happens with the error term? And error term, so error, it's of the order integral the length of our contour of C epsilon eta, which tends to 0 because epsilon tends to 0. So there is no error, error disappears. Because we deal here with summing the lengths of the contour functions, which are probabilities which are of order of a constant, and the error term is summing the length of the contour of something which is epsilon small. So it's much smaller. So basically these terms, if contour is length 100, they are of order 100, and this is of order 100 epsilon, so it's much smaller. And when we integrate, this is of order constant, this is of order epsilon. So it's So we deduce the following identity, basically for any triangular contour. So it's kind of, if you sum H alpha, if you integrate it with the weight plus, so what was it? It was AB. Yeah, so if you integrate it with the weight plus 1 here and minus 1 on the bottom line, then it's the same as H tau alpha integrated plus 1 on this side and minus 1 on the right side. And it would be the same as H tau squared alpha, again the same thing, minus 1 on the left side, plus 1 on the bottom side. Now let's just check. Well, I mean that's basically it, because we now only have to check that the contour integrals of these two guys are 0, and it follows from these relations. Because what is the so let me position my, well, let's position triangle like that. So it's A, B. How was it? ABC. A, B, C. So what is the contour integral of a function f on the triangle ABC? It's integral over CA. So when we go CA, well, DZ. When we go CA, DZ is just equal to 1. We go in the real direction. So it's just integral CA of f times the length. So it's Z. Now, plus integral, if we go AB, we go in the direction tau. So with AB, we get f dz, we go in the direction tau. And integral BC, f dz will go in the direction tau squared. So it can be rewritten in terms of such integrals that you get -1 on one side and +1 on another side. Why? Because if you look at the real part of this guy, so the real part is integral f CA plus what is the real part of tau? It's -1/2, I think. Yeah, -1/2 integral f. Yeah, maybe, you know, yeah, maybe I'll just write it in the following way. So it's so we have what? So I'll just write it as such sum. So I'll write that it's integral BA minus integral CA of f plus integral of yeah, let me just write it symmetrically, integral BC minus integral BA of f plus integral CA minus integral BC of f with coefficients. So what do I need to do to get the coefficients correct? I think I need to so I want to get coefficient 1 in front of CA and coefficient tau here, coefficient tau squared there. So it's already it's clear that I should put I over square root okay AB so okay tau so AB minus BC minus wait a second, AB minus BC, so put here minus I 3 over 2, and we put here CA minus, so wait a second, so CA should be 1, yeah, okay. So it's an exercise with using the fact that cube root of unity is minus 1/2 plus I square root of 3 over 2. That this identity holds up to Littlewood convention. Littlewood convention is that you can change sign and multiply by 2 whatever you wish. So it holds up to multiplicative constant and change of sign. Yeah, I think actually we are correct. So CA gives 1, tau you get AB minus 1/2. Yeah, I think we are done. Yeah. And those are exactly the things with which we worked, where we can change H alpha for H beta, etc., etc. So those are exactly the things with which we worked. So basically the corollary is that if we do it for H alpha, corollary is that integral contra integral of H alpha so contra integral of H alpha will be the contra integral of, which time do I have? I still have. So contra integral of H tau alpha, and what happens if I plug in? Well, let's maybe right now contra integral of H alpha. It's the sum of 3 such things: minus 1/2 integral BA minus integral CA of H alpha plus etc. Now, this thing for H alpha, we know that we can change index and we change the size, so it's minus 1/2 integral, so we rotate everything, so it's integral BC minus integral BA of H tau alpha, and so on and so on. And that would be that would be the same formula integral for H tau alpha, only what we did, we now rotated the triangle. So we, instead of BA we have BC, instead of CA we have BA. So to get contour integral we need to multiply by tau, because we rotated everything. If we rotated everything, Z is rotated by tau, we need to multiply it by tau. So basically what happens is that we have BC here, so we start CA, we have BA, so we have to divide by tau. Yeah. So hence our lemma can be written as contour integral of H alpha is integral to 1 over tau contour integral of H tau alpha is equal to 1 over tau square contour integral of H tau squared alpha. So the reason is that if you write the same discrete integrals, contour integral over triangle, you can write as a sum with different weights, like 1/2 plus I cube root of 3 over 2, etc., etc. Then you play these games, and then you get the same weights only for rotated function up to this. So maybe this part is more visual, but in principle, if one wants to really do the rigorous proof for contour integrals, one has to check that identity. And now we are essentially done, because what now happens? What is the now check that contour integral of our function f is contour integral of h1 plus h tau plus h tau squared, and contour integral of h tau is tau contour integral of h1. So contour integral of h tau is tau contour integral of h1. Contour integral of h tau squared is tau squared contour integral of h1. So we get that it's contour integral of h1 plus tau h1 plus tau squared h1. So it's contour integral of h1 times 1 plus tau squared, and it's equal to 0. And exactly the same with g. So it's contour integral of h1 plus tau h tau plus tau squared h tau squared. So it's contour integral of h1 plus tau h1 plus tau squared h tau h1. So it's contour integral of h1 times 1 plus tau squared plus tau to the power 4, which is again 0. So all the complications which are here are because we deal with the basis not of two vectors 1 and I, but cube roots of unity, which is redundant. There is one redundant vector, and so it's because of that we have to write all the sums. But it's essentially clear that once we got our Cauchy-Riemann equation, we can do some pictures like this. So we can pass to we can pass to contour integrals, and it's clear that if we have some contour integrals, we'll have exactly analytic functions. So the only thing which can go wrong if we confuse somewhere the sign, so I didn't know why I wrote here tau squared and tau, then you get anti-analytic functions. You get not Cauchy-Riemann, but you have Cauchy-Riemann with where one sign is changed. But you are basically, you don't have much choice what to get. Okay, so this is the proof. Now maybe a few remarks. So it's a bit different from all other proofs we have. So far we discussed uniform spanning tree and loop arrays and the walk. We discussed later Ising model, and in all those cases we have an exact harmonic or exact analytic functions. So here we still have an exact combinatorial bijection, but it doesn't give us exact Cauchy-Riemann equation. It gives Cauchy-Riemann equation where part of the term has shifted, so it gives us with an error term. So in a sense, here it's much less rigid thing, and in a sense, it shows that you are not required really to have exact identity to pass to a limit. So here there is no exact analyticity on a lattice, but we still can pass to a limit and not shedding so much blood. So it might be that in other models which we cannot do yet, there are observables which are not exactly analytic, but approximately analytic. But then, of course, it's much more difficult to look for them, because if something is exact harmonic, well, you can check numerically that it's exact harmonic, then you know what you're proving. And if something exact harmonic, then probably there is a combinatorial proof by bijection. If something is approximate harmonic, then there is a much wider variety of methods to prove it. Now, the fact that it's more rigid, unfortunately, means that we don't know how to do it on square lattice. And if you try to transport it to square lattice in some way, this proof, so the attempts have been made, then you are sort of First, even if the proof ever would work, it would have square root of 3 popping up from the square lattice. From hexagonal lattice it pops up just for a very simple reason that we have this coefficients tau and square root of 3 is an imaginary part. In square lattice you will be forced to have some probabilities which have ratio square root of 3, which cannot be then exactly true on a discrete level, so it should appear in something more, so I would be rather pessimistic. It's more realistic to try to do some kind of this proof for bond percolation on triangular lattice, but again there it's too rigid, it doesn't work. Now if you have this observable Cardis formula, of course you can show convergence to a SLE6. You can actually you can has Wendelin spoken about locality of SLE? A little bit. So one calculation one can do about SLE6 is that SLE6 is local. So if I do SLE6 in this domain, or I do in a domain where a piece is removed, SLE6 doesn't see it before it hits it. So it's the very same with percolation. Percolation interface doesn't see this part until it hits it. So if you have a myopic end going on a lattice, unless it hits, it doesn't see. In Ising model or in UST, it's not like that. If I fix this part, it slightly changes probabilities elsewhere. So one can do calculation for SLE. So the easiest way to do, the original way to do it was that you draw a different Lovni revolution here, and you see what happens if you commute them. First, you draw this and then draw evolution, and the other one you draw evolution and then draw this. And when you write the commutator, it turns out that it has coefficient kappa minus 6. So if kappa minus is equal to 6, then you can commute the order in which you draw. So SLE6 is local. It doesn't see what you've drawn elsewhere. And for other SLE, if you draw on something, then it shifts your guy. So it's clear already that if there is a convergence to SLE, it should be SLE6. One can also check that for SLE6 you have Cardis formula. Or vice versa, you can start with Cardis formula and check that it is SLE6. Now, for this you only need one thing, so I will do it next time because, or maybe I don't know, maybe it's a good thing for the exercise. So suppose that I draw the interface from here, and the interface, it has yellow on the left and blue on the right. Then what does it mean that this interface, so it goes something like this, that this interface hits this point? It means that there is blue on the right of it, so there is blue crossing from here to here. And there is yellow on the left, so there is a yellow crossing from here to here. Now, what do we know about in a triangle of probability that yellow thing lands somewhere on this interval? It's just length of this interval. So if we take the leftmost if we take Vermont, we take really this point where the yellow and blue touch, this point by Cardis formula is distributed linearly, uniformly. So one can check that for SLE6, if you run it in half plane and map to triangle, that the point where it first time touches this interval is distributed uniformly. So it's, or you can vice versa get this from Cardis formula. So basically, Cardis formula, what does Cardis formula tell you? So let me redraw it one more time. So suppose I'm growing SLE, and suppose I have this picture and I grow SLE to infinity. So what does it mean that there is a yellow thing like this? It means if I grow my SLE, which so that it's yellow on the right and blue on the left, it means that my SLE jumps like that, and then it jumps right over these 2 points together. So it cannot touch here, because if it touches here, then it ruins this yellow thing. So probability of this crossing is exactly the probability that my interface jumped over both points at once. So you see it can be written in terms of SLE, Even better, the probability for a point inside can be written even better. And then you have an exact formula for it. The exact formula for it is phi, which is integral of something something. And then if you plug in it and do the usual power series expansion trick, there will be this ugly function phi. But the next coefficients, there will be like phi plus 1 over z phi prime something plus 1 over z squared phi prime prime. And phi prime are relatively nice functions because it's already derivative of this, so you can do all the calculations. So either we discuss it next time, or we'll put it maybe in the exercise. So how crossing probability is written in terms of interface, and can one deduce that it's SLE6? And there was also Schwarz-Christoffel.
Okay, we can try and do it on Friday during this.
Yeah. Okay. So now there is an exercise session. So Friday this week, which is what is it? What's the day? Friday is 22nd. Friday 22nd, long exercise session. Then there is no course on Friday 29th. It's 22nd Friday. 18 plus 4, yeah, 22nd. And then Friday, which is 22 plus 14 is 36th of April, which is May 6th, is the next lecture. So we skip one lecture next week. Okay, questions? So unfortunately, it's a bit less logical and more robust thing, rigid thing than the proof for UST. So it somehow works by a piece of combinatorial magical coincidence, and that's why it sort of has evaded so far the attempts to generalize it. Okay. And now there are exercises for Nicolas Courien's course. Yeah.